Oh, great. Let me do a little wrap up of last week and a little foreshadowing of what's coming. It's Sunday morning. It's a little past 11 or so. We're coming right to the end of a 2-week period that we looked at both chapters 5 and chapter 6. And in fact, as I look through the grades right now, there's still quite a few people who haven't done, say, the 30-point chapter 6 exam yet. And I think many of those people will do that over the next 12 hours before it closes. When I look at the grades, week 6, 50 points per week, you should have about 300 points or more, and 62% of the class right now does. That's actually down. We've been running at sort of 75%, so I get another 5 or 6 people who get themselves another 30 or 40 points. I probably have back up to that 75% level. I've got 9 people right now who are over 400 points. Somebody's at 455, by the way. Really good score. Keep that up. So nearly a quarter of the class is just still doing just very well. So congratulations to you. What you did this week was you learned how to use the calculator to find areas under the normal curve that look like this. And so that's a neat trick, but what's it good for? Well, I think you realize that those areas under the curve are associated with probabilities. This one in particular is the probability that if you reach into this distribution and pull out one of the values of the random variable, just like reaching into a sack of marbles and pulling out a marble, that area represents the probability that that value lies in that area out there. So a neat trick, like I said, but you've done enough problems to see that that allows you to solve some probability problems that you wouldn't be able to solve with classical probability techniques. You really have to be able to find these probabilities on the normal curve, on the student's t-curve. Later we're going to introduce the chi-squared curve and the f distribution. And in fact, that's what I wanted to say. If you think it's a neat trick, in chapter 13 you're going to be doing exactly the same thing to conduct what's called an ANOVA test. In chapter 12 you're going to be doing exactly the same thing to conduct a goodness of fit or an independence or a homogeneity test. In fact, for the remainder of this class, every chapter you're going to find a way to do exactly that type of calculation and carry out different tests that do different things in statistics. In fact, we have kind of come to the end of descriptive statistics, and in fact maybe we've been at the end of it a long time and been in this quasi land of probability. But starting this week or next, depending on how you want to look at it, we're doing inferential statistics, and you will find yourself using the calculator to find areas under the curve and the associated probabilities, just like that. So chapter 7, it's kind of a tipping point. You've got 6 chapters, chapter 7, 6 more chapters into the program. And chapter 7 is an interesting time right now, and it's an interesting chapter because the title of the chapter is the central limit theorem. Now, the central limit theorem is not about something at the center. In fact, central in this case means central to statistics. It's not central to inferential statistics. It is a theorem, and that theorem is at the heart of everything we're going to do. And in fact, for the next few chapters, every time I can, I'm going to remind you that at the basis of whatever particular test or technique we're executing is the central limit theorem. I'm probably then going to forget to do that, but if you pay attention, here on out, all the way through chapter 13, the central limit is in the middle of what you're doing. Central limit's hard to understand. Central limit is hard to say, if you believe that. I'll show you, because I'll tell you what the central limit is, or at least one version of the central limit right now. Let's imagine there's a population over there. And I'm going to reach into it and I'm going to grab a sample of size n, okay? And with that sample of size n, I'm going to find the mean of that sample, and I'm going to write it down. x bar 1 is equal to whatever it is. Okay, throw that sample back, get another one, also of size n. Calculate its mean, write the mean down. X bar 2 is whatever it is, throw it back. Get a third sample, find the mean, write it down, throw it back. I'm going to do that probably for about 30 times. It doesn't really matter if that, especially if that population is normal. If it's normal, then almost any number of samples will produce the result I'm going to describe in just a second. If it's not normal, you got to be over the magic number of 30. Might be good to have 300 means down here. So what have I got? I got writing on an envelope, that envelope has 300 means. If I make a dot plot, what I see is a distribution of those sample means. That is in fact called it's called the sampling distribution of the sample means. And one version of the central limit theorem is, get this, that the mean of the sampling distribution of the sample means is equal to the population mean. Okay, I'm going to say that again. This is again just one version of the central limit theorem. There's a version for the sums, not the means, but the sums, for the proportions, not the means, but proportions, for the variance as well too. But for the sample means, the central limit theorem says that the mean of the sampling distribution of the sample means is equal to the population mean. Okay, no joke, 5 points extra credit for anybody who sends me an email or text message with a little voice recording of you saying that. Right? The mean of the sampling distribution of the sample means is equal to the population mean. Yikes. So again, kind of a neat trick and a neat relationship, especially when you go further to say there's another relationship between that population and the sampling distribution of the sample means. And that is if the variance is sigma squared of the population, the variance of this sampling distribution is sigma squared divided by the square root of n. Okay? So if the population is some distribution with a mean right here and a standard deviation like this, or a variance like this, then a standard deviation, I should have said, then the sampling distribution is a distribution like this, mean at exactly the same place, standard deviation equal to this standard deviation divided by the square root of n. Okay. So that's what's coming. That's what's coming. The last thing I wanted to talk about just briefly was your discussion. Gosh, I understand. I feel like I understand you people a lot better. I sort of thought you were a singularity, and now I'm pretty certain. If you haven't read through all of the discussions in this improbable events discussion, do so. It's really instructive. It reminds me of that, what is that, a State Farm commercial where the tagline is, "We know a few things because we've seen a few things." Well, you people know a few things because you've seen a few things. That was really some good input. I don't actually want to talk about it now because 2 or 3 discussions from now we're going to come back to that and talk about why is that the case, that improbable events seem to occur. And there's many answers to that, and many are already there. I'll tell you one just so I can tell you a story. One reason is that many things are perceived to be improbable that are not. I had several people say that holes in one in golf are improbable, and I think Shannon said, "Oh, maybe not so." I got to tell you, I saw a hole in one in my foursome last Monday, and the guy who hit it, it was his 5th hole in one, and everybody in the foursome had had at least one hole in one, and everybody in the foursome had seen 5 holes in one. So, you know, if you're a golfer, yeah, they're rare, but they're not earth-shatteringly rare. And that, I think there are some other examples in that list of things which are perceived to be maybe just based on your life expectancies, but maybe aren't so rare. But there are several other answers. For this week, there's another discussion. It's actually an experiment that I'm going to have you do. So read the instructions and get off on that. Let's get back on that 1 module, 1 chapter per week, and try to stay on that for some time. All right? So keep it going. Hope you're having fun. Thanks.